I'm going to argue the idea of software intelligence is flawed. You might remember from yesterday that we had this complexity-based measure of intelligence, like counterintelligence, and it's measured with respect to a fixed UTM. And that IXC is the most intelligent agent according to Occam's razor if it uses the same UTM, right? So they've got matching notions of complexity, then according to Occam's razor, IXC is optimal, but you never know if you're going to get the right interpreter, right? So this undermines all the previous optimality claims for IXC and resulted in the paper yesterday. But I would argue that IXC also reveals a sort of a deeper flaw in the idea of software intelligence, and that is that what software does depends on how you interpret it, the hardware that interprets it. And you can think of it like this nested structure of software mind interacting with the world through an interpreter. And it's sort of like almost a disembodied notion of a spirit, a bit like sort of a disembodied version of what Joshua was talking about with animism yesterday. I really like that talk, by the way. But taken to its extreme, this kind of characterizes software as immortal, and people have talked about this. Hinton has spoken a lot about, immortal versus mortal computations, and that's a really catchy way of framing it. And as the next keynote is about this very topic. In fact, Alex Orobia and Tristan have formalized mortal computation, and I really like this direction because I think that immortal computations don't exist. The reality is that software is the state of hardware, and the distinction between hardware and software is kind of reminiscent of some ideas from 16th century philosophy, namely Cartesian dualism, which was the idea that Descartes thought that you had two substances, mental and physical, and that the mental affected the physical through the pineal gland, which acted like an interpreter, and then the physical affected the mental the same way. Now, there were problems with this that people identified pretty quickly, and today, philosophers talk about things like embedded, extended, inactive, embodied cognition. But when we talk about software intelligence, if AI is the sort of engineering branch of philosophy of mind, then we're still talking about dualism in a way, and I'll call this computational dualism because it kind of mimics this mental and physical substance idea by talking about software interacting with the environment through hardware, which is actually like the pineal gland. Now, I'm not saying this is just straight up another instance of the mind-body problem. This is a slightly provocative name, but and software and hardware are very useful categories when we talk about applications and actually building the world products, but it has thwarted our ability to model upper bounds on intelligence. If we want to make claims regarding objective behavior, not the subjective interpretation by a UTM or something like that, we must avoid computational dualism. We need to formalize hardware and software together. And that is how this whole project started. So if the interpreter is the problem, then we need to get rid of it. We need to formalize the environment and mind as a single thing. And I mentioned that philosophy has moved on from dualism. They now talk about the mind as a process within the environment, as an interaction between organism and the surrounding world, as cognition is something that is inactive rather than simply passively sort of thought off in some ether. And this idea, this inactive cognition, is often seen as at odds with a computational description of the world, because computation usually talks about interpreters. And it's a great point. If we have an organism as an interpreter, we have to talk about, well, where does the organism end? Where is the boundary between the organism and the surrounding environment? What's part of the interpreter, what's not? Why is one interpreter chosen and not another? To get around that kind of problem, we need to move the interpreter outside the environment. We just say, the interpreter is the laws of physics, and what we're dealing with here is a mind and environment together. This is an attempt to unify computation and enactivism by bringing in something called pan-computationalism, the idea that everything is computation. Now that can be, depending on how it's interpreted, a controversial idea. Here I'm just referring to a very basic notion of computation as things like cause and effect, as information processing. So a very weak notion of pan-computationalism. And so then, just to give an overall summary of this paper, we start with the question of how do we formalize objective rather than subjective behavior. As yesterday, we're building upon that same formalism, but here the emphasis is really on the body as an abstraction layer, that implements a formal language. Yesterday I talked about a sort of a post-structuralist take on the environment as every fact is the set of states in which it holds. So this is saying that a body is implementing a language in the same way that I was talking about an aspect of the environment yesterday. And then goal-directed behavior is a task written in that formal language, which is to say we don't talk about goals separate from body by default. We talk about them as embodied goals. I'm also going to talk about them as separate, but they'll come in a bit. Because then we characterize intelligence as adaptability or sample efficiency and generalization. This whole project started as an attempt to solve Chalet's ARC dataset, then formalize that aforementioned disembodied goal. So now we can find the ideal embodiment to approach a particular problem or task, and then prove an upper bound on intelligent behavior characterized in this manner. So you could think of it as finding the ideal body for a purpose. Now, like ARC, this is impossible to build. You have to search an infinite space of bodies, but it's useful because we can then reason about objective rather than subjective upper limits on behavior, and it has potentially very different implications with regards to things like safety, and it gives us a clear target to iterate towards by identifying the ideal body. Now, you don't have to worry about the math for the sake of this presentation. I'm just showing you that's here, and I'm showing you these diagrams that I showed you yesterday with the correct labels here. Now, you might recall that a program is a set of states. Truth of a declarative program is determined with respect to states. So this is how, if we want to talk about a body as a language, as an aspect of the environment, we can talk about the body as a set of statements that can be made by taking sets of declarative programs. And then we can say that, well, when a body is in a particular state, as in I have my arm up here, this would be like a statement, X, in a formal language. And that constrains what else the body can do to this extension of X, right? You could think of X as an input or a beginning position, and the extension as the possible responses to that, the outputs. And so that lets us formalize tasks and talk about things like Chalet's ARC dataset. Now, if we're talking about statements as inputs and outputs and constraints, then input is like a constraint on the possible outputs. We can use a second statement as a policy and constrain the outputs to just correct outputs by some arbitrary notion, like one of the ARC problems. Now, this kind of harkens back to some notions of embodied AI from people like Heidegger and Dreyfus, and there's this great quote from Rodney Brooks, which says, "The best model of the world is the world itself." And the reason I bring this up is because really what I'm just doing is constrain the possible outputs. I'm not making any comment about possible world models or anything like that. And the reason I want to frame sort of goal-directed behavior and inputs and outputs this way is so I can talk about embodied generalization. So you could think of a hammer as a policy, and a hammer can generalize to different tasks. It could be a weapon, it could be a paperweight. This is just an intuitive example. And then we can talk about learning as being given a small task, a small set of examples, and generalizing to a much bigger task. And you could think of an organism's history as different tasks. Now, you recall these past results from yesterday's presentation. The weakest constraints expressed by the weakest policy is the optimal choice, but that weakness depends on the embodiment we choose. And we want to know which body is best if we want to identify a superintelligence. So we can measure the utility of choosing weaker policies for a given task and a particular embodiment by taking the difference between the extent, the weakness of the weakest and the strongest policy. That is to say, if I give you a task, like press a red button, being more intelligent is not going to make you much better at it. You're just going to be pressing the red button. But if I give you a task to play a game of chess, there is a lot of potential for you to adapt and improve. And that's what this expresses, is your potential utility of intelligence here. And then, to find out what the best possible embodiment is for a particular task, we need to be able to switch embodiments. So we need to be able to represent the same task in different, using different embodies. So I've got this notion of an uninstantiated task, which takes which is a function from possible embodiments, that is a set of declarative programs, to tasks in that set of using that set of declarative programs. So it takes a body, returns a task. And this allows us to take the same task and compare it across different bodies. And when we do that, we can identify the one that maximizes this utility of intelligence. And that's what I then show as the upper bound, that if we are allowed to just use any body, that is any abstraction layer, then the upper bound is the body that maximizes that utility of intelligence. Or it's the most intelligent body for a particular purpose expressed by the uninstantiated task. Now, downside of that is, as I mentioned, it's incomputable because you'd have to search infinitely many bodies, but it does let us talk about things like superintelligence and what an upper bound would look like. And it kind of suggests that AGI might be a little bit safer than some of the rhetoric might indicate. That if you have to search through an infinite set of bodies, this is probably going to slow you down. There's no shortcut, really. But it gives us a target to iterate towards, a target to aim for. That if we want to solve something like the AIC dataset, this is how we find a set of primitives to work with that convey, as shall I put it, a strong inductive bias. And I think, I know yesterday when Joshua was talking about the animism thing, he was talking about, computational functionalism as sort of a prerequisite. I think ideas like his cyber animism would work really well with this. I think if we would just need to, essentially formalize how different states of hardware interact to talk about, these animist spirits that he was getting at. Since people requested more eyeballs. This is pretty much the end of this part of the talk. I do have a poster as well that's related, which is about the hard problem of consciousness and abstraction, again based on the same formalism. And it relates also to my papers last year and the year before. I've been formalizing some of Michael Levin's ideas with multi-scale competency architectures, trying to integrate that with the work of Alex here and on the more computation stuff. And I have been going to philosophy conferences and talking about things like causal learning and specifically a neuroscientific notion called reafference, which is where this would tie consciousness stuff. And here is a preview of that poster. That's everything.